All right, folks, welcome back. It's me, Mr. Hess, again. I'm here to teach you another section of Chapter 9, which again deals with circles. In Section 4 that I'm going to cover today, the title of this section is Inscribed Angles. Okay, so I did speak about in our last section about what an inscribed polygon is. Well, it isn't a big stretch then to teach you what an inscribed angle is. So let's start with a picture of a circle like this. Now, previously, the only type of angle I had talked about within a circle was where the vertex of the angle is right here at the center itself. You know, like when you're cutting up slices of an apple pie or something, you start at the center, work your way out. So the radius is used for the sides here. And remember that an angle like this was called a central angle, because, of course, it has its vertex at the center of the circle. Okay, but what I want to show you today then is a different type of angle that does not have its vertex at the center, so they don't call it a central angle. Instead, this one, as you can see here, is going to stretch back even further. So instead of the vertex ending right here at the center, the vertex goes all the way back to the back of the circle like that. So an angle clear in the back like this with its vertex on the circle itself, this is what we're going to learn about today and what is called an inscribed angle. Inscribed. Remember, to inscribe means to fit inside. So as you can see, this angle fits perfectly nice and neat inside of the full circle, instead of stopping at the center of the circle like the central angle did. Okay, now if you think of this arc out here kind of like a bow, you know how when you shoot a bow and arrow, you know, when you pull back on the bow, the string of the bow is going to form that angle there. Well, if you compare the central angle, which only draws the bow back to the center, versus if you pull all the way back to here, you might be able to figure out that the two angles here are not going to be the same. For example, in this picture here, if this angle is, let's say, 50 degrees, that's at the center, that central angle, the further back you pull on this, the smaller and smaller that angle starts to get. Okay, so this angle you might have figured out already is smaller than 50. And you might say it's been pulled back twice as far. You know, this one was only pulled to the center, whereas if I pull all the way to the back of the circle, instead of pulling just to a length of the radius, you're pulling almost like a length of a diameter, you know, twice as far back. So if I'm going to pull this twice as far back and it's getting smaller as I pull it back further and further, then this angle here, the inscribed angle, you may have figured out, is then exactly twice as small, or only half the measurement of this central angle. So if the central angle here is 50, this angle then would only be 25 degrees, half of the 50. Remember earlier we also learned that central angles and their arcs have the same measure. So if the central angle is 50 degrees, the arc is 50 degrees. So based on this whole idea, now if I eliminate the whole idea of the central angle altogether, so if I get rid of my central angle like that, and just work with my inscribed angle, then you could see that we could come up with a rule that would say that an inscribed angle is always going to be only half the measure of its intercepted arc. Okay, and this in fact is our first theorem. It's theorem 9.4 on your list of postulates and theorems. And it simply states that all inscribed angles will always be half the measure of their intercepted arc. Or you could look at it backwards and say that the arcs will always be twice as big as the intercepted angle. Okay, so if you understand that concept, every postulate and theorem I'm going to cover in this section always relates right back to this theorem, theorem 9.4. The idea that an inscribed angle is half of its arc. Okay, so let's look at another theorem then. On your list of postulates and theorems, there's a theorem 9.5. And in theorem 9.5, they just simply say this. Let's say you've got a circle, and I'm going to create an inscribed angle, maybe like that. Do you see then that here's the vertex of our inscribed angle? It worked its way out, and it hits this arc. See that? So that would be referred to as the intercepted arc. The arc that was created when the angle intercepts the circle. Now they say, well, what if I did this then? So if I call this one angle 1 and this one angle 2, what relationship do you think they have? If you guess that they're congruent, angle 1 and angle 2 are congruent, you are correct. In fact, we could do this all day. I could start here at this end of this arc and go up here and then back down to that end. There's a third angle that's congruent. If I go out over here, there's a fourth angle that's congruent. But you'll notice all four of these angles are all inscribed angles, first of all, and they all share the same arc. See that? 1 comes down and hits the ends of this arc. 2 hits the same arc. 3 hits the same arc. 4 hits the same arc. So if they're all sharing the same arc, then they all have to be how much of that arc? Yep, you guessed it, half. Okay, so they're all going to be congruent then as a result as well. So in this picture, 1, 2, 3, 4, all those angles are congruent. Okay, so try to keep an eye out for that. If 2 inscribed angles share the same arc, they're going to match. There's also a theorem 9.6, which I'm going to draw a picture for down here. Let's say that this is the center of the circle on this one. And on this one, I'm going to draw a diameter going through that center. And then I'm going to draw an inscribed angle that comes out and hits each end of the diameter. So like this. I might have the angle go up here, touch the circle, and then come back down and hit the other end of the diameter. That wasn't a very good line. Sorry, let me try that one more time. That one should look more like that there. Okay, so now look at this inscribed angle that I made that has its vertex on the circle. It comes out, it hits each end of the diameter. It's going to be a special angle because if it's hitting both ends of this diameter, then the arc that it intercepts down here is an arc that hits each end of that diameter as well. And that means that this arc that goes from one end of the diameter to the other, a diameter cuts a circle in half, so shouldn't that be a semicircle, half of the circle, 180 degrees? And if the arc is 180, then any inscribed angle that hits that arc, according to our theorem 9.4, should be half, and half of 180 is 90 degrees. So this is a little trick that you could always do. If you ever make an inscribed angle that comes down and hits each end of a diameter, it's guaranteed to make a right angle. And the diameter itself then caps off a right triangle even. So of course, anything that we've learned about right triangles, maybe the Pythagorean theorem, wink wink, could be used on a problem like that. A squared plus b squared equals c squared. Okay, but it's a guaranteed way to make a right angle. And this is theorem 9.6 in your list of postulates and theorems. Okay, and I got one more theorem I want to cover here. Of course, it's going to be theorem 9.7, the next one. And in this one, let's say we've got a circle. And in our circle, let's suppose that we have a quadrilateral that is being inscribed inside of the circle. Remember, again, we just talked about inscribed polygons, which are polygons then made up of chords. So when I go from edge to edge of the circle, edge to edge of the circle, edge to edge of the circle, and then I'm going to cap it off with one more. So, and this has to be a quadrilateral for this one, okay? So it has to be an inscribed four-sided figure, quadrilateral. Okay, it won't work for anything higher or less. But as a result, then, as you can see, we have some inscribed angles as well. You know, an inscribed angle has its vertex on the circle. So there's one inscribed angle there, and here's a second one with its vertex on the circle. Here's a third one down here, and of course a fourth one over here. Okay, it turns out, according to this last theorem, Theorem 9.7, it states that the opposite angles in our inscribed quadrilaterals, so like 2 and 4 and 1 and 3, have a certain relationship here. Turns out then that the opposite angles, like 1 and 3, are going to add up to 180. 2 and 4 add up to 180. I mean, we already learned when we talked about quadrilaterals that all four angles of any quadrilateral add up to 360. So that makes sense, you know, that 180 plus 180 is going to add up to 360. But not all quadrilaterals, when we learned about quadrilaterals, not all of them had that unique capability where the opposite angles added up to 180. Okay, in this case they will though. And I know it's true because, again, it's going to go back to this idea that an inscribed angle is half of its arc. Okay, so I'm going to use some colors here to help illustrate this one, because this one gets a little tricky. For right now, let's just focus on 1 and 3. Let's show that they add up to 180. Okay, so when you follow angle 1 out, do you see that angle 1 is an inscribed angle that hits this arc that goes all the way from there to there? So angle 1, see it, comes out, hits that big arc. So we know that angle 1 will be half of that arc. I don't know what that arc is, and it doesn't matter. You'll see why it's not going to matter. Because now if you look at angle 3, you follow it out, it hits that arc. 3 comes up, hits that arc. And notice the pink arc I just made there for angle 3, that when you put the pink together with the green, together they make a full circle. And we know a full circle is 360 degrees. So if the arcs are going to add up to 360, the angles that were only half of their arcs, right, are going to only add up then to 180, because 180 is half of 360. Okay, and then you see you could do the same exact reasoning for 2 and 4. The only difference, of course, would be my yellow and green would shift around a little bit. You know, 2 would come out and hit that arc. 4 comes out and hits the other part of the circle, the rest of the circle. But again, the 2 arcs come together and make a circle. So if the arcs add up to 360, the angles are only going to add up to half of that, because inscribed angles are only half of their arcs. So that's a neat little trick you can use then if you ever have a quadrilateral, a four-sided figure that's inscribed perfectly inside of a circle. So it's all of its vertices are on the circle. All right. Those are our theorems. Okay, so now I just want to go ahead and try some problems based on these ideas. Okay. Let's start out with a problem like this. Let's say that there's the center of the circle, so this is a diameter. And let's say that I've got an angle here that's 42 degrees. And let's label some of these points. Let's call this A, this B, this C. Okay, and some basic things, first of all, that I want you to be able to do. First of all, if I said, okay, look at this picture and name for me an inscribed angle. Okay, something as simple as that. Just name the inscribed angle. Okay, remember, an inscribed angle has to have its vertex on the circle. Okay, so at first glance, this 42-degree angle that's at the center is not going to work. Okay, that's at the center. Okay, but you'll notice, for example, back here at A, that point is on the circle, and if you follow it out, see, it's got two sides that hit the circle as well. So the angle BAC is an inscribed angle. That's this angle right here, BAC. Okay, be careful. If you're thinking, okay, I want to name this angle B up here, notice that as it comes out, it stops. It stops at the center there. One side of it didn't finish. So the full angle isn't fit inside of the circle, you know. To be an inscribed angle, we need it to go all the way out to the edges of the circle yet. So if I were to extend this out yet, now you could say that point or angle B up here would be an inscribed angle. But if I leave this out like it was originally written, that is not an inscribed angle. Okay, so there's my inscribed angle. Now if I ask you to also name the intercepted arc. Intercepted arc. Okay, I'm just simply saying if that's the inscribed angle, what arc did it hit? Okay, we were naming this inscribed angle. You follow it out. I hope you could see it hits that part of the circle, that arc. So you would say that the arc BC is the intercepted arc. Okay, now, what if I said, what's the measure of that intercepted arc? Now, this just goes back to something we already learned in a previous section, that if a central angle is 42 degrees, then the arc that it hits is going to be the same measure. So that's also 42 degrees. So the arc that it hits is 42. But more importantly, now let's go back to our inscribed angle. You should now be able to figure out the measure of the inscribed angle. So if the arc out here is 42, this inscribed angle clear back here that hits that same arc, remember we learned in this section, is only going to be, the inscribed angle is only going to be half of its arc. So the measure of this angle back here should only be 21 degrees, half of 42. Just as a little bonus question for this problem, what if I said, what's the measure of arc AB? Now keep in mind, we did have a diameter, AC, that went right through the center. Diameters are your friend. Okay, diameters always cut a circle in half. And half of a circle, of course, you know, is how many degrees? 180, yes. So if all the way from A to C up here is a semicircle, 180, take away 42, and then that's what's left here. So 42 taken away from 180 leaves you with 138 degrees for the measure of arc AB. And then, of course, in this section, they would probably relate that back to some kind of inscribed angle yet. You know, so what if in this picture, what if I drew, you know, something like this? And we created a new point down here, D. So you see this angle down here at D? Okay, you should be able to find the measure of that angle D. If you follow it up here, do you see that it hits that arc I just had you find? That 138. It's an inscribed angle, so it's not a matching 138. It's not the same. If it was at the center, it would be. So this angle right here is 138 at the center. Okay, but if I go all the way down here now, that should only be half of 138, which is what? 50, 65, 69? 69 degrees. Okay. Let's try another. Okay, in this picture, let's say that there's the center of the circle. Again, there's a diameter. Diameters are your friend, don't forget that. Okay, but on this picture, let's say that this arc out here is 100 degrees, and they want you to find the measure of that angle right there. All right, now if you're thinking, oh, it's a half of 100, it's 50. No, it's not. Be careful. Follow the inscribed angle out, and you'll notice it hits this arc right here. So if I knew the arc, I could find the angle, the inscribed angle. Currently, I don't know the measurement of that arc, but it can be found. Remember, a diameter is your friend. It cuts a circle in half. Half of a circle is 180. So I know that this arc I want to know plus the 100 has to equal 180. So all I have to do is take the 100 away from 180, and that leaves 80 degrees for that arc. Again, that's not my final answer, though. If the arc is 80, the inscribed angle clear down here that hits that arc would only be half of that. So half of 80 is 40. There's the measure of the missing angle, 40 degrees. Okay? Okay, on this next one, let's say that we've got a picture like this. 1, 2, 3, 4, 5. We're going to call it penta. P-E-N-T-A. Penta. Because after all, it's a pentagon. And let's say that that's a regular pentagon. You remember that regular means that it has all equal sides and angles. So that means all of these chords that make up the pentagon are all going to be equal. All those sides. Okay, and I'm going to draw one more line though across like that. All right, now you should then be able to figure out some measurements here for me. Let's start with the measure of arc PE. The measure of this arc right here. Arc PE. Now, don't forget that we learned in a previous section that if all of these chords are the same, then so are the arcs. The arcs all have to match. So this arc, that arc, that arc, all those arcs are going to be the same. And notice that all of those arcs make up a complete full circle, which we know is 360 degrees. So if I take 360 and split it up equally 5 ways, penta, 5 different ways, then I'll have the measure of each arc. So 5 goes into there, let's see, 7, carry the 1, 2, 72 degrees. So each of these is 72 degrees, 72 degrees, 72 degrees, 72, 72. Or there's my answer then to that one. The measure of arc PE is 72 degrees. Okay, that's going to help me with some of these other answers as well. So on this next one, and be careful on these. You know, that was a measure of an arc. Here I want the measure of an angle. So measure of angle PTN. Follow those letters in that order. PTN would be this angle, PTN. Okay, notice it's an inscribed angle. It has its vertex on the circle. And when I follow it out, I see that it hits not 1 but 2 of the 72s. See that? So it hits an arc that is a total of 144. See that? But keep in mind my inscribed angle is only going to be half. Okay, so an inscribed angle is always half of its arc that it hits. So you follow the inscribed angle out, it hits 2 72s. So half of that would only be 172. So that angle is 72 degrees. So this angle right there, 72 degrees. Okay, let's try another. Let's say they want you to find the measure of angle PEN. PEN is this angle right there, PEN. It's another inscribed angle. If you follow it out, it hits a 72, a 72, and another 72. So it hits a total arc of 3 times 72. Okay, so you can look at it that way. You could say, all right, 72 times 3 gets me up to 216 degrees. But again, remember, the inscribed angle is only going to be half of the arc. So if that full arc of 3 72s is 216, half of 216 leaves me with 108 degrees. So this turns out to be 108 degrees. Because 108 would be half of 72 times 3. Now there was another way to find that answer, by the way. Don't forget, I did have a theorem today that also talked about when you inscribe a quadrilateral, four-sided figure. And when I drew PT here, notice this is a quadrilateral that's been inscribed inside of the circle. So, and earlier, the previous question just had you find 72. These are opposite angles in that quadrilateral. So remember that theorem said that these two should add up to 180. So if you realize that, you could have just said, all right, 72 taken away from 180 is 108. It would have been a little quicker than doing all this work. Either way, though, doesn't matter. Both are correct. They both give you the same result, 108. Okay. I got one more type of problem I want to show you here. There's our circle, and let's say there's the center of the circle. And let's say we've got a couple of chords that are crisscrossing like that, and let's say this is 82 degrees, this is 66, this down here, and let me try drawing that again one more time. Now I'm purposely missing the center. There, that looks a little more accurate for my measurements. Okay, we'll call this A, B, C, and D. Let's go ahead and draw in some segments across like this as well. All right, now I'm going to ask you some questions about this one. First of all, let's just start with this question. How big is the measure of arc AB? If you look up here, it's that arc right there is what I'm asking about. And I just want you to simply notice that I've given you 1, 2, 3 measurements here. And the only one missing that completes the circle is that one up there. So all we have to do then is simply understand that a full circle is 360. And we're going to take away from that 360 all 3 of these. You're going to take away the 66, the 82, and the 44. And whatever's left then would have to be that top measurement for arc AB. Okay, I'm going to do that on my calculator here. And I find then that we're only left with 168 degrees for this one up here. Okay, now that I have all the arcs, okay, I should be able to figure out any of these other remaining answers that I might ask about. Like, For example, let's say I want to know the measure of angle ACD. ACD, that angle. Again, notice I put angle, not arc, angle. So we follow that, ACD with vertex at C. I'm talking about that angle right down there at C. Notice it's an inscribed angle. It has its vertex on the circle. So if I follow it out, I see it hits this arc. That's 66 degrees. So that means the inscribed angle is not 66, but exactly half of it. So if I take 66, cut it in half, do you see that leaves me with 33 degrees for that angle right there. Okay, what about angle ABD? Angle ABD. So again, if I follow them in that order, ABD, ABD is this angle right there. It's another inscribed angle. I follow it out. It hits the arc that was 66 again. So it's another inscribed angle hitting the same arc. Guess how big it is? You guessed it. It's a matching 33. That was one of our theorems that we had, remember, in this section. If inscribed angles share the same arc, they're going to be equal in measure. So that would also be 33 degrees. Okay, what about the measure of angle BDC? BDC is this angle right there. It's an inscribed angle with its vertex on the circle. I follow it out. I see it hits the arc that is 82 degrees right there. So that means it's not 82, but exactly half, right? So half of 82 would leave me with 41 degrees. So this angle down here is 41 degrees. You probably guessed it. Yeah, there's another 41 degree angle. It would be the other inscribed angle up here that hits that same arc of 82. So that's 41 as well. Okay, now it kind of leads me up to a final question here. I'm going to call this point right here, that's not the center. You know, let's call P the center. But you see this point down here that I'm going to call E? Okay, let's say I wanted to find then the measure of angle AEB. AEB. Now AEB is this angle in here. But be careful. It's not an inscribed angle. See how its vertex is not on the circle? It's not down like, you know, like here or there where those were, or up here. And it's not at the center of the circle either. So don't think, oh, I could just go up here and see it hits the 168 and go, oh, that must be a 168 degree angle. Nope, wrong again. Okay, the only way really to find, well, I shouldn't say the only, but the way we're going to find that last angle right there is to use the idea that it is the only missing angle left in that triangle. See that triangle? We've got a 41, we got a 33. That's the last angle left of that triangle. And we know triangles always add up to 180. So if I take 41 and 33 off, okay, that angle should be whatever's left. What is that? 74 off of 180 would leave you with 106. So that angle right there should be 106 degrees. For right there, 106. Okay, so not related at all to that arc up here, is it? Although I will say this. There is another way to find it where you don't have to know these. Okay, it turns out that if all I had, and I'm going to start erasing some stuff so all this clutter doesn't throw you off, but let's say all I had was a crossing X pattern. Like this, not even that across there. If I just had an X, see that chord, this chord crossing at an X? Okay, I already know that vertical angles should match, so I already know then that this angle is also going to be a matching 106. Okay, those are vertical angles there. But I could find that 106 initially by just using the two arcs that these hit. So when you follow that X pattern, see how when you follow this angle up, it hits the 168? And then if you follow this one down, it hits the 44. Okay, you don't even need the 82, you don't need the 66 over here. Okay, those two vertical angles that I know have to match hit these arcs out here that are 168 and 44. And it turns out the 106 that they're supposed to be here, you can get it by averaging these together. So if you take 168 plus the 44 and then divide that by 2, if you do the average of the arcs, then it'll come out to the 106. I mean, look, 168 plus another 44 is what? 212. And half of 212 is 106. Okay, so that's a little shortcut that you could do. If you ever have any situation where, again, you got a circle, you just make some kind of X pattern like that. And again, it doesn't have to go through the center. Like there would be the center of the circle, let's say. Okay, and if I know the opposing arcs, the ones that are opposite of each other, then you can find the angles. You know, so like if I knew this was 172 degrees for this arc, and then if I knew that this arc over here was 54 degrees, then these two angles in here that are formed when you follow those arcs in, those two vertical angles that I know already match, are going to be then the average of these arcs. Okay, so if I take 172 plus 54 and divide it by 2, that's what the angle is going to be. So 172 plus 54 gives me 226. Half of that is 113 degrees. So each of these should be 113 degrees. Okay, that's a little shortcut, a little trick you could use. All right, I believe I have shown you enough to prepare you for your homework in this section. So in section 4, for homework, I'm having you do page 470 and 471, problems 17 through 27, and problems 37 through 45. Okay, and again, I want to remind you to make sure you put your name at the top of your paper and label the assignment so I know which one it is. And if you need any help, don't forget you could get a hold of me. I'm not holding office hours anymore, but if I can still do a personal Zoom meeting with you if you need to see how to do some problems. So just contact me either by email or you can send me a text through Remind. And then we can set up a little Zoom meeting and I can work with you. Otherwise, I will see you then for section 5. That's my next section in chapter 9.